Well, Sebastian is a PhD student in the Systems and Network Security Group at the Vrije Universiteit. And the research group did some interesting work on problems in chips.
Yeah. So let me take it over. Okay, so today I'll talk about Riddle, Rogue Inflate Data Load, a paper that we wrote in collaboration with J.H.A. from Saarland. So, okay, well, most of the authors are from our group, so the FUSEC group at the Vrije Universiteit. So it's Stefan van Schaik is the main author of the paper who did all the work, but he couldn't be here today, he's in the US at the moment. So, well, let me just tell you about, real Rogue Inflate Data Load, side channel attack on, or microarchitectural attack on Intel chips. So you might have also heard about this in the media. Intel's PG-13 name for this MDS, or microarchitectural data sampling. So there was a bunch of media attention in May when we released this, and you might also have seen this last week when we had a big story on Intel's disclosure process, which is deeply flawed. So first, I'd like to tell you, quickly introduce the speculative execution attacks, how these work. So this is a very quick overview, but just to give you an idea. So basically, modern CPUs speculate on data because memory accesses are slow. So they try to batch memory access together or throw them out like earlier to get so that they don't stall on memory reads or writes. And this is supposed to be kind of invisible to the user, but in practice, what might happen, so this is an example of the Spectre, for example. So suppose there's a branching condition, like if input is smaller than 42, and input has not been read from memory yet, the CPU issues a memory read for input, but while this is going on, it already speculates and takes one of the branches, depending on what the branch predictor decides, and might actually pull this into the caches, which you can leak with the traditional cache attack. So this is briefly how Spectre and these kinds of attacks work. So let's talk about cache attacks. So modern computers have a memory hierarchy like this. So you have very fast CPU registers, then you have different layers of cache, and then main memory. And basically, the lower you go here to this storage is like the slowest one, and CPU registers are the fastest ones. And well, to introduce some terminology, so if some data that you want to read is available in the cache, so L1, L2, L3, we consider it a cache hit. Otherwise, if it has to be fetched from main memory, it's a cache miss. So here's an example of a traditional cache attack, the flush and reload cache attack. So basically, what you do is allocate an array of memory, and then flush this with like a CL flush instruction. So you walk through it so that you make sure that it's not in the cache. So if you try to access anything here, it's going to be a cache miss. Then suppose you want to leak something from a victim. So a victim reads something from whatever table, a secret value. This will be pulled into the cache. And of course, now when you try to reload it, you walk through the array again, you access it, and you'll see, okay, this one is slow, so it's from DRAM. Next one is slow, it's from DRAM. But this one, since it's been loaded in by the victim, it's going to be a cache hit. So it's going to be much faster than the other one. So you can detect what other people on the system have basically pulled into the cache. So this is one of the building blocks for like modern speculative execution attacks. Let me focus on Meltdown because it's very similar to Riddle, basically, or all the MDS attacks. So as you can see, it consists of, well, similar steps. So you have like the flush and reload step, but in between there, you have some other code. So basically with Meltdown, what you can do is load any kernel memory address, and it will be pulled into the cache, and then you leak this through a cache attack. So again, walk through the probe array, flush everything so that it's not in the cache. Then with an attacker, you basically you read a kernel address. Of course, normally this with seg faults, you need to suppress this fault somehow. So here we use TSX, this hardware feature to suppress faults to invalid addresses. But this thing will be executed speculatively and pull it into the cache. And then, well, you dereference this thing from the what you leaked so that you actually offset it into the probe array. And then you can just do the reload part of flush and reload to, again, to leak what the value is at the kernel address, basically, that you want to leak. So this is briefly how Meltdown works. In practice, it might be a bit more complex than this, but this is basically what we build on top of. So there's, of course, since this became public, there's been a bunch of mitigations. So we have KPTI, kernel page table isolation, array index masking, XOR masking. So I'll briefly explain kernel page table isolation. So typically on Linux, the address space layout of a program looks something like this. So you had user space and you had kernel space mapped into the same address space, just for efficiency reasons. So when you do a system call, you don't have to remap the whole address space. Well, the problem is, of course, you can, with Meltdown, you can leak the stuff from kernel addresses. So the solution for this was to, just split up the address space. So you have one with only the user space and another one with user space and the kernel in it. So this seems to fix it, right? So this is the official mitigation. Well, we start to look at this, okay, what can an attacker still do with all these mitigations in place? So suppose we have a system, here's my desktop at the university, which has all these mitigations in place, so PT inversion, well, all kinds of things, KPTI enabled, whatever. Yeah, what can we still do as an attacker? Well, let me show you how the Riddle thing works in practice. So first we print etc shadow. As you can see, I'm not a normal user, I can't access this file. Then, of course, just to show what the value is of the etc shadow, do sudo cat and show it. So this is the password hash of the root user of my system. And here we execute the attack, which repeatedly starts up the password utility and then leaks this through our attack. And well, this goes through slowly like this. And initially this took 24 hours, but in the end you leak the whole password hash, which is kind of bad. So meet rogue in-flight data load, or Riddle, as we call it. It's a new class of speculative execution attacks that don't depend on addressing. So yeah, I'll explain this a bit more. So first of all, you might wonder who is affected by this. Well, we bought a bunch of Intel and AMD CPUs and started testing. So after we found this, we started trying out, okay, how vulnerable is everyone? Well, we found out that every Intel CPU, almost every Intel CPU since 2008 is vulnerable. So we bought a bunch of Intel CPUs from every generation and built a nice IKEA rack, nice cable management, right? So yeah, so we have like this nice setup with like every Intel, major Intel generation. And well, turns out that it works on all Intel, mainstream Intel CPUs since 2008. So we have this nice check mark, it works on everything. Then at some point, Intel announced that they're releasing a new generation, the 9th generation, which supposedly had in-silicon mitigations against Foreshadow and Meltdown. So they're like, okay, that's an interesting target, let's have a look at it. So we bought it. Too bad we got it like 1 day after we submitted the paper to S&P, so we couldn't include it in the initial submission. But turns out it just works on it. We just run the box and everything works. So let's add that to the list as well. We also bought some AMD CPUs to try out if this works on AMD. We have not been successful in getting this to work on AMD yet, and we actually tried a lot, but yeah, they seem to be safe. So we have this nice picture of Riddle inside, runs great on Intel. Okay, but so we know that we can leak some stuff, and but where do we actually leak from? And this is kind of, initially we didn't really know what we were leaking. So we had this POC that we developed, and we saw we were leaking stuff, but where from? So typically, like Meltdown and stuff leak from the caches, but we quickly realized that this is stuff that was not actually in the cache. So where are we actually leaking from? Well, so the caches are well documented, well understood, and yeah, we don't leak from caches, but what else is there to leak from? So turns out there's a bunch of other internal CPU buffers, as you can see. So you have the line fill buffers, the store buffers, and load ports, as you can see here. And these things are not really well documented, but so what we see is that we actually can leak from multiple different internal CPU buffers. So that's why you consider it a new class of attacks. This is, yeah, so it's a new class, and you can leak from, kind of exploit this in different ways, leaking from different buffers. So we started reading the manuals, and we couldn't, like, most of these internal buffers are not really well documented at all. They're like sometimes mentioned offhand in the manual. So we had to actually start looking at patterns to see how these things actually work. So luckily, I didn't have to read these patterns, but Stefan actually went through all these patterns one by one to find out how these internal buffers actually work. Then, well, of course, we did some experiments to verify that the hypothesis that we had that, for example, the line fill buffer, that we actually leak from the line fill buffer. So if you're interested, you can read this in the paper. We have a bunch of these experiments. And the conclusion was that the primary variant we had actually leaks from this thing called line fill buffer. So yeah, for this presentation, I'll skip the more details on these buffers. So typically, we have a short explanation on this, but to keep it brief, I'll just skip that for now. So, well, we know we can leak from this buffer. So what can we actually do? How can we exploit this? So we came up with some nice ideas. Well, we know that we can leak so-called in-flight data. So anything that's available in these buffers, we can, with some, if we try hard enough, we can actually leak this stuff. So the challenge is we need to get some sensitive data in flight. So enter the confused deputy attack. So typically, well, as a normal user, you can't really read any sensitive data. But of course, you can trick other utilities on the system, the more privileged utilities, to actually read this data and pull it into one of these buffers. So one thing we noticed, by invoking the password utility, you actually have, like, the system has to read the etc shadow file to try to authenticate the user. So if you want to change your password, yeah, of course, the operating system has to open this file. And, well, what we can do is we can set the affinity of process, so we can narrowly select on which logical core a certain process runs on Linux, for example. And, well, it turns out that these buffers, like the line fill buffers, are shared between hyperthreads. So if we have two processes, one attacker and one victim, sharing a hyperthread, we can actually leak stuff from the victim. And, well, that's exactly what we do here. We run the password utility, load the etc shadow file into the line fill buffer, and then leak it through our Riddle attack. So the first challenge, getting data in flight, well, that's easy. We invoke the password utility, which you can do as a normal user. So, and the other thing is, like, okay, actually leaking data. So how does this Riddle attack work? So let me show you. This is basically the code for the attack. At the first instance, it looks like really similar to Meltdown, right? So the only difference in this code and the Meltdown one I showed you earlier is that this is a null pointer instead of a kernel address. And, well, to tell you a fun story, like, actually how we found this was a bug in a code. So we were trying to reproduce something else, and there was actually a bug that did a null dereference, and we magically leaked stuff. So this, it's sometimes good to have bugs in your code. You'll accidentally find some important stuff. Sorry, what's the question? Serendipity. Yeah. So, yeah, let me walk through this. So, okay, again, the first step, like the flush and reload, we have this probe array that we flush. We walk through it so that things are uncached. Then we start a transaction and try to dereference a null pointer. Well, normally this would segfault the program, right? But since we're in a transaction, we can do this without, we can suppress the error, basically. Yeah, and, well, of course, like, I have to mention that this, we use the TSX hardware feature here, but we're also able to do this without this hardware feature. So I'll explain this a bit more in detail soon, but you can use demand paging to get the same behavior. So we read from null pointer, and then in speculative execution, you will use this byte as an offset into a probe array. So it will read whatever is in the line fill buffer here, for example, and you will use this, it will pull it into the cache, and then you can use a cache attack to leak this. Yeah, that's it, basic, and then, yeah, we walk through the array again and time everything, and see, hey, this is the value that we actually read from the line fill buffer. So we have a primitive to leak data now. So seems fine, we can get access to anything on the system. Well, turns out it's not that easy. So it's, we have this nice, well, I think Herbert Boss came up with this, like, Riddle is drinking from a fire hose. So you get all this data basically garbage, so it's hard to distinguish what is actually what you want to leak or if it's some other garbage data. So yeah, you get whatever is in flight on the CPU. So maybe, yeah, you can consider this like snooping on a telephone line, that you have to know the exact time when it is in the, in flight to be able to get some useful data out of it. So we have to do some post-processing on the data to actually get what we want to steal. So we came up, there's basically two alternatives here. So one is you do some synchronization, so you know the exact time when it is in these buffers, or the other one is to just do some smart post-processing. So first of all, so we came up in the scenario that the synchronization thing is not really easy to do because we, for example, in the password example, we can't change the binary at all, so we can't add any kind of synchronization primitives there. So, well, we had to opt for post-processing. And a nice thing that you can do with the password utility, you can repeat this a bunch of times. So we can do a bunch of measurements and basically stitch them together to get a more clear result. So how can we filter the data? So again, to reiterate this, we want to leak from the etc shadow file using the password utility. The first line is typically for the root user. This is the default configuration. So if you open your own etc shadow file, you'll probably have the entry for root in the first line of the file. So, and this file always starts with root colon. And well, as you can see, this is a screenshot from my system. So we can do something like use a prefix matching. So we already know that this should be in there. So if we match something, a new byte, we can learn a new byte. So suppose we match a measurement that starts with root colon and something after it, we consider it a valid measurement. If there's no match, we discard that measurement. So let's, I'll give you an example here. So we start with the known prefix, then we do a measurement, and it turns out, okay, if we leak something else, it's not consistent with what we know. So let's just discard this. Then we do another measurement where the initial bytes are consistent with what we already know. So what we do is assume that this is a correct byte. Okay, then we have another measurement which we discard. And now, like, since we already know this, we fix this and we have a new measurement that's consistent up to that, and then we add the next one, and so on until we get the whole string. In practice, it's a bit more involved than this. There's some nice assembly hacks because this has to be done in speculative execution, but if you want the full details, read the paper. So what we can do is leak the root password hash from unprivileged user, which is kind of bad, right? So, but okay, you need local execution access on the machine, so let's extend this a bit. And of course, cloud computing is super hot at the moment, so let's do a cloud attack. So suppose you have a victim VM in the cloud that you want to attack. So what we need to do is get an attacker VM that's co-located with this victim VM, so on the same machine, and basically so that they share the line fill buffer, so you have two hyperthreads that are shared on the same core. This is possible to do, by the way, on some cloud providers. So I think most of the major ones actually don't share hyperthreads nowadays, but some of the smaller vendors still do this. So on the victim VM, well, again, we can leak the etc shadow file. Let's take that as a target because it's an obvious target. Typically, a victim is running an SSH server, right? So how do we get the data in flight? We can't invoke the password utility here, but what we can do is set up SSH connections, which also turns out to read the etc shadow file. So we basically do the same attack, but over the network. So when we start try authenticating, it will load the etc shadow file into the line fill buffers at some point. And well, the content is now in flight, and we can do the exact same trick. We can leak it using this exact same program we already discussed. So we run the Riddle program, and we're able to leak the etc shadow file of a co-located victim VM, which is also super bad, right? It's, yeah. So we have some more examples what we can do. So we can leak some internal CPU data, so page tables. We can circumvent ASLR or KSLR, for example. We also had an arbitrary kernel read using a Spectre gadgets. And we were also able to do some leaking from the web browser. So let me talk a bit about the next step after. Like, so we had a cloud, And well, I skipped the arbitrary kernel read for now, but basically you invoke a Spectre gadget and then you can do an arbitrary read. So these haven't been fixed as far as we know, but still it was possible at some point to do this. So the web browser, everyone runs a web browser on the computer, right? Most people at least. So as I explained already, so we were using TSX for this, but from the web browser it's hard to kind of run something like this from JavaScript. You don't have access to TSX. CL flush for the flush and reload part might also not be available, so we have to come up with some ideas here. So yeah, it's not really feasible, this thing. Well, for no CL flush, I think this is easy to solve. There's other cache attacks, so we can do evict plus reload, which I won't go into detail here, but it's a cache attack that you can do from JavaScript, for example. We don't have TSX, which is a minor, well, it's kind of an issue, but as already explained, we can do demand paging, which is this feature in the operating system where it doesn't map in the actual page until you try to dereference that page. And at that point, so if you dereference invalid memory, and then the operating system basically suppresses the fault. So here is some code for a more portable version of our attack. So first you do an evict and reload. Well, you evict the buffer. Then you have to allocate a new page, which is demand page, and then you dereference this value into a leak buffer like we already had. So you load that into the cache, and then you walk through this probe array again and leak it. So it's very similar, but you don't have the transaction stuff around here. So you replace it by demand paging, which most modern operating systems support. And you can actually trigger this from the web browser. And the nice thing is, for this is C, of course, but we can generate basically exactly this stuff from WebAssembly. So we have a proof of concept with WebAssembly that can leak data. So, well, here's a demo. So this is the SpiderMonkey JavaScript engine. So I don't have the UI here because you got a lot of noise. So you won't have something that's as fast as this. But as you can see here, we can leak like a string. So we have another program running on the computer writing this to memory, and then we can leak this from the web browser, basically. So let's talk a bit about existing mitigations that we have for the speculative execution attacks. So there's three mechanisms. So one is to inhibit the trigger, which is basically stop speculation or add fencing, and you might be familiar with the red Pauline compiler pass to kind of defend against these kinds of attacks. The other one is to simply hide secrets. So we consider KPTI falls under this. You split up the address space. You can do something like array index masking or flushing the caches. So this works. So this is for Meltdown, right? This is for some of the Spectre variants, and this is for the Foreshadow attack. Another way of mitigating these things is simply to disrupt the channel of leakage. So disable timers so that you can do something like flush and reload. So most of these, so the first two here, the first two fail because they assume addressing. So they all do something to the addressing to make it impossible to actually leak stuff. But what we already saw is that we leak from null pointer. Like Riddle doesn't really rely on addressing at all. It just pulls whatever is in flight and leaks that. So messing around with the addressing doesn't really prevent Riddle attacks. So after we disclosed this, Intel started working on some mitigations. Already before that, I guess. So I don't know how long they've been working on these things. And basically, so there's two variants of this. So the more practical variant I described here, we used hyperthreads, but you can also do this in a same thread setting with speculative execution. There's a hardware fix for this. So Intel brought out microcode updates, which repurposed the var_w instruction so that it flushes the affected buffers. For CPUs that don't have microcode updates, they provided some weird assembly snippets that look like this, that are supposed to flush these buffers. Well, later turned out that these are not really don't work that well, as you might have read. Then for the cross-thread one, so the one with hyperthreading, it's not really easy. You can't insert an instruction in between when you access something, when you leak it, because it's going on concurrently. So Intel basically proposed this weird scheduling scheme where two co-located hyperthreads are never in the same security domain. So this is already a simplified version of this scheduling scheme, right? So, and as far as I know, no one has implemented this yet. I don't know if any of the cloud providers do this, but I'm pretty sure like the overhead will be huge for this kind of stuff. So basically what we suggest is to disable hyperthreading because it's broken by design, right? It's horrible. And of course, this is kind of now also the official Intel mitigation after, so last week we came out with, we released some of the variants that were still under embargo, and they're simply not really, it's not really possible to fix this. So you can now disable hyperthreading using a model-specific register. So while we were working on this, of course, we got a lot of information from the patents. So Stefan made this nice diagram of the Intel Skylake architecture with a nice overview. And so since we looked at line fill buffers and whatever, but as you can see, there's a bunch of other internal buffers that might be used to leak stuff. And so as you can see, like the mitigations that Intel proposed, they flush only the affected buffers, right? But this is like another spot mitigation. It doesn't fix this issue at the fundamental level. You will still have the issue if just look at how many buffers here. There might be you might be able to leak something from whatever here, and then the current mitigations don't work.
How does AMD do that?
So it turns out that AMD is not as aggressive with some optimizations, and they don't share. So I don't know exactly. So there was something with line fill buffers that they don't. It's just partitioned in a sane way, so that you can't leak something from other hyperthread or SMT thread. So internally, I don't know how AMD does this. So my colleague Stefan has more knowledge on this. So yeah, it's too bad that he isn't here to explain this.
Were they smart, or was it coincidence that they got it right?
Yeah. So our hypothesis for this is that Intel has just been super aggressive with optimizing stuff, right? So they want to squeeze every last bit of performance out of it. That's why they also the performance has been better than AMD for the last many years, right? And AMD hasn't gotten to this hyper optimization stuff, which is kind of lucky. I think it's a lucky guess for them, but there might also have been some thought behind it, right? So who knows?
It could also be because it's patented and they can't implement it.
Yeah, that might also, yeah, so that's also the issue, right? So these things are patented, so they have AMD, it works differently from this, right? But still, they could still do some kind of optimization but they seem to be safe for now. So it might also be that people haven't been looking into it as much as Intel's hardware. But yeah, who knows? So the attack that I showed you, the leaking the password thing, it took 24 hours, right? So you might ask, is it really realistic? Who has access can run this for 24 hours and leak stuff, which is, it's meh. This attack is a bit unrealistic. So luckily we have some good master students. So we had a master student do a term project on this, and he managed to optimize it. So here I have a recording of this, and this is in real time. Let's see, does it start? Yeah, no, it start, okay. So basically you can see the password hash leaking here. And the time, so it was in 10 seconds, which is, so kudos to our master students. They're actually really, really good at this stuff. And this was embargoed until last week because it uses a slightly different technique that Intel, last minute, told us that, okay, please don't go public with this because we don't have any mitigations for it at all. So now they have a mitigation, which is to disable TSX, but yeah. So the thing is, these issues need to be fixed at a fundamental level. So they have, we see them one by one popping up, and I guess later this year and next year, we'll see a bunch of variants of this popping up, doing the exact same thing, circumventing their mitigations. Which, by the way, so their original, the VerW mitigation they had, that flushes the buffers also did not flush the buffers, right? So they put random data in it, which turned out to be sensitive data. So this was also something that was embargoed until last week. So I don't know what they're doing there, but yeah. So but let me talk about the disclosure process a bit. So of course, we need to talk about this. So we discovered this on September 11th last year, and then the next day reported to Intel because we realized, okay, this is serious. Then we started writing a paper, and of course we submitted it. And later we got some information from Intel. Oh yeah, there's also other people who have found similar issues, and we got put into contact with them. And well, only Georgie wanted to collaborate on a paper, so we added him as an author on the paper, and he basically also added the arbitrary kernel read exploit using Spectre gadgets. Then we had an embargo set for May 14th, if I remember correctly. And then, well, there was, so of course, some talk with Intel here, but mostly silence. And then all of a sudden, a few days before going public, Intel comes with, oh, there's also more finders that found similar issues. And, oh yeah, by the way, could you also embargo these things because we haven't fixed them yet, basically. And, well, so later we found out that Intel simply lost, like, the POCs that we sent them. I don't know how they're able to do this, like, at this point we got like the internal Intel documentation on their fixes, and we were able to get some leaked microcode updates like BIOS, so we were able to test out their mitigations and just run the exact same things we sent them in September, and we were still able to leak stuff with the supposed mitigations on. Well, so here's a word cloud of a bunch of other finders. As you can see, there's a lot of names in here. We've been trying to collect all these names and credit everyone on our website, mdsattacks.com. Also last week, we were able finally to publish our test suite and proof of concept attacks. So they're also now available. You can just look at all these things. So we have nice example implementations of some of these attacks and all the different variants. Yeah, question?
Is your presentation available?
Yeah, so this presentation is available on the website. Also, well, not this exact version. I can also put it up on the website, but a similar version to this is available on the website. And there's some more information about like what we released last week and the whole story about how Intel screwed up with their, with their embargo stuff. We also have a nice tool which you can run or works on Windows, Linux, Mac OS, also Mac OS, I think, where you can see which hardware features are enabled and disabled and how vulnerable you are to these kinds of attacks. So, in conclusion, well, Spectre Meltdown, we thought it was just one mistake that Intel fixed it. Well, yes, again, of course, there's some new other attacks. We have Riddle, a new class of speculative execution attacks that can leak from internal CPU buffers without being aware of the addressing. So there's many more buffers other than caches in the CPU that we can leak from. And yeah, as I already said, it does not rely on addressing, so it's very hard to mitigate using any of the common mitigation strategies. And we can leak across all security domains, so this works for leaking from other virtual machines, for example, from Intel Secure Enclaves to SGX, and well, you name it, basically. So security domains don't matter for this thing. So if you like, you can follow us on Twitter, and you can visit the website MDS Attacks, where we have like the Riddle paper and also the Fallout paper from other people, which is also a similar kind of attack. So with that, I'd like to thank you for your attention and open the floor for any questions. Yep.
Very strong story, thank you. What would be your advice to us and what would be your advice to Intel?
Well, to you two is, well, for normal use, so first of all, I think most normal users are not really at risk for these things at the moment, but who knows if someone can, like we had this master student optimizing this to like a 10-second attack. If someone can do the same thing from the web browser, right, we're all screwed. So basically, like, you have to disable hardware features and like enable all the mitigations. I think then you're like fairly safe.
Slow down.
Yeah, exactly. So Apple did some benchmarks on this, right? So the performance overhead can be up to 40% for some workloads. But so these things add up, right? So all the mitigation for Spectre, Meltdown, for Riddle, like MDS things, So I think there were some benchmarks also last week for this. So it starts adding up, right? And then, well, to Intel, yeah, I don't know what to say to them. Like I think they're probably trying their best, right? But the current like microarchitectures are simply like they have all these issues, so they simply have to design them from scratch. Who knows with their like new CPUs coming out in a few years, they will probably fix these issues. But until then, you have to enable some of like these defense and take the performance hit, I guess. Like, yeah, I think that's the answer for that. Any other questions? So, yeah. Any other questions? Okay, thank you very much. Yeah, have a look at the website. I'll make these slides available there, and so you can have a look at them. I'll also add some of the slides that I skipped for now that have some more details in them. And, well, you can, of course, also read the paper there, but it's very technical, so just a warning. Okay, thanks.